All right, so our project was detection and classification from RF fingerprints using machine learning techniques. I'm Cole, and I worked on this project with Millen and Seth. So this project attempted to extend the findings of the paper Micro UAV Detection and Classification from RF Fingerprints using machine learning techniques, and we did that by improving neural network classification accuracy. We focused on the detection and classification of micro unmanned aerial vehicles, UAVs, using radio frequency fingerprints of the signals transmitted from the remote controller to the micro UAV. Significant features of the waveforms captured were fed to several machine learning algorithms for classification. And on the left, you can see kind of a high-level overview of that process. This dataset contained RF signals from drone remote controllers of different makes and models. The RF signals transmitted by the drone remote controllers to communicate with the drones were intercepted and recorded by a passive RF surveillance system, which consisted of a high-frequency oscilloscope, directional grid antenna, and low noise power amplifier, which you can see on the right. All the drones were idle during the data capture process. All the drone remote controllers transmitted signals in the 2.4 gigahertz band. There were 17 drone remote controllers from 8 different manufacturers and 1,000 RF signals per drone remote controller, each spanning a duration of a quarter millisecond. So in the baseline paper, significant features of the waveforms, those features being skewness, variance, entropy, kurtosis, were fed to several machine learning algorithms for classification. You can see the performance of those 4 algorithms on the left. The neural network algorithm used in the paper performed the worst with an accuracy of 60%, compared to the KNN algorithm, which had an accuracy of 97%. The authors of the paper hypothesized this poor performance was because they failed to optimize hyperparameters of the neural network properly. And so our project aimed to improve the performance of the neural network by properly tuning those hyperparameters. So this is a high-level description of our model. We adapted this model from the paper RF-based low SNR classification of UAVs using convolutional neural networks. Our model was designed for image classification with input sizes of 128, 128, and we had 17 output classes. It comprised of 3 convolutional layers followed by ReLU activations, max pooling, and progressively increasing output channels. We had 2 fully connected layers with 256 and 17 output features, and we had a dropout layer between them. The forward pass involved convolution, activation, and pooling operations, followed by flattening and dropout regularization. And then finally, we had a softmax activation, which generated our class probabilities. So the following histograms show the training results for our baseline model. The histogram on the left showed the predicted label distribution, and the one on the right showed the actual label distribution. In our very first run of the CNN, we were able to achieve a training average loss of 2.22 and a training accuracy of 59%. These next histograms show the testing results for the baseline model. Again, histogram on the left shows the predicted label distribution, and the one on the right shows the actual label distribution. We achieved an average testing loss of 2.22 and a testing accuracy of 59%. So to transition from our baseline model to our final model and optimize our hyperparameters, we experimented with increasing the resolution and number of epochs, adding more fully connected layers and dropout for those layer outputs, and applying batch normalization to all convolutional layer outputs. We discovered that adding one more fully connected layer with dropout for this layer output resulted in the best performance of all the trials we ran. Our average training loss here was 1.904, and we achieved a training accuracy of 91.225%. The average test loss here in the testing results of our model was 1.947, and the testing accuracy was around 87%. This was a great improvement over the 60% accuracy in the baseline from the micro UAV detection and classification paper that we read, and our 59% accurate baseline CNN. Our accuracy rate of 87% achieved through the tuning of hyperparameters in our CNN model helps to close the gap between the neural network architecture and the 3 other machine learning algorithms in the first reference paper. Therefore, we met our goal of improving the classification accuracy of the neural network model in the paper and improved performance by 20%. Thank you, and let me know if you got any questions.